Hello, welcome to 9.2. We are going to be talking about tangents, and just a definition of the word tangent. It is actually a Latin word, and it's derived from the Latin word tangere, which means to touch. So tangent means just to touch. Alright, so if you think about that, a tangent line is just going to touch a circle. So let's just go do some definitions here. The first is secant. Secant is a line that's in the same plane as a circle, and it intersects the circle in exactly 2 points. Now, a secant results in a chord. So we talked about a tangent briefly already. It's a line that's in the same plane as the circle, and it intersects the circle in exactly 1 point. Now, the point of tangency is the point at which the tangent intersects the circle. So it just touches the circle in one spot. So here's a picture for you where the line MN creates the chord MN, or the segment. That is a secant line. And then I have the line FG, which touches the circle at point F, which point F is the point of tangency. So our first theorem is 9.4. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Just like when we could make a radius be a perpendicular bisector of any chord going through a circle, we can also make a radius that intersects at the point of tangency that is also perpendicular to that line. So because there's infinite number of radii in a circle, we can do a lot with them. So now let's talk about the law of contradiction. This is, teenagers like to contradict people, so you hopefully will like this one. If an assumption leads to a contradiction, then the assumption is false and the negation is true. So there's actually a proof, yay, on page 376, okay, and it's going through the definition of tangent. If the line AB is tangent to the circle O at point A, all of these things will be true. Now, the reason why there's an assumption in the first place is because we don't know if it's true. So if we make the assumption, then we can try to prove it to be true. And it turns out that it is not true. Okay? Now, we are, like I said, pretty much done with proofs. But just like we had the law of deduction, this is just another law that we would use in proofs. So I don't want you to worry too much about this particular theorem. I do want you to know that the law of contradiction exists and what that theorem is, but we just won't be practically using it. Okay, so the next theorem is if a line is perpendicular to the radius at a point on the circle, then the line is tangent to the circle. So this is the converse of theorem 9.4, which talked about if a line is tangent to a circle. So here's a circle, and here's a line that is tangent to that circle. If I drop a radius that is now at that point of tangency, I'm now saying the line is perpendicular to the radius. Then the line is tangent to the circle at that point of tangency. So the next theorem is tangent segments extending from a given exterior point to a circle are congruent. So if I have a point outside of the circle, I can actually draw 2 tangent lines that will touch a circle from that point to the circle. So if you look at page 377, of course, there's the proof for it, and the picture is very helpful. Here's what the picture looks like. So there's a point out there in space in the same plane with circle A, and they're calling it point X. So I can draw two tangent lines from point X that will touch the circle at two different points of tangency. So here's one of them, XM, the point of tangency is M, and then the other one is XN, where the point of tangency is N. So this theorem says that XM and XN are tangent to the circle, but we need to prove that they are both congruent to each other. So this theorem says that that is the case. Okay, so look over that proof. Couple more definitions. A common tangency is a line that is tangent to each of two coplanar circles. And then a tangent circles are coplanar circles that are tangent to the same line at the same point. So easiest way to understand these two definitions is to look at a picture. Okay, so common tangents are classified as internal if they intersect the segment joining the centers. So let's look at a picture. The segment OQ is the kind of the internal area of these two coplanar circles. So if I draw all four of these lines, A, B, C, and D, are all common tangents. Just we have internal common tangents and external common tangents. So B and C, those lines touch on the external of both circle O and circle Q. But if you look at line A and line D, yeah, is that right? Line A and line D, those both cross that segment OQ. That means those are internal common tangents. So A and D are common internal, and B and C are common external tangents. Let's talk more about what happens if the circles are touching. So circles can actually be tangent to each other. They can be internally tangent, which means there's a smaller circle inside a larger circle, and they touch at just one point. And then there's externally tangent circles, and they're on opposite sides of that common tangent point. So let's look at a picture of that. Okay, so if you look here, internally tangent circles are going to be circle M and circle N. They are internally tangent, and they're tangent at the same point. Then there's circle M and circle P. They are both touching at the same point, and those are externally tangent circles, as well as circle N and circle P. Those are also externally tangent circles. So with three circles, we have two externally tangent and one set of internally tangent. For your whisk summary, I have drawn a figure for you. I'm going to kind of talk about it a little bit, but there's going to be 4 problems that I want you to show all your work and submit to me. So here is the figure. It's pretty complicated looking. I don't want you to be intimidated at all, but what I do want you to be aware of that these degrees of and segment lengths are not to scale. So if you look at one and you think, well, that looks longer than what I'm getting mathematically, go with what you're getting mathematically. Okay, so it may not be that it may not look exactly accurate, and I don't want you to be frustrated by that. So what you get mathematically is what I want you to submit. So basically the segment KH is a perpendicular to the segment MC, and I think that's the only thing that isn't as obvious as some of them. It just doesn't look super perpendicular, but it is supposed to be. It's not a bisector, it's just a perpendicular. So go ahead and write down the information, and then the 4 problems are on the next slide, and I will see you in class.